Okay, so big thank you to Arlene Hoffa and the biochemistry class for their crushing it in chemistry Valentines. That was super cool. One of the things we want to take a note of is that when we think about reactions specifically, there's kind of a structure or a format for how they're represented. So we always have our reactants on the left and our products on the right. And so if we take this example, which is the combustion of glucose, we can actually see here that we have a molecular formula for glucose. And again, these are subscripts, and that's important to differentiate from coefficients. So for example, coefficient in front of oxygen tells us that we have 6 diatomic oxygens, right? Or another way of saying that is 12 total oxygens that are this reagent. And then we have a couple of different ways we can represent glucose. So if you were to actually see it, it would be a rather thick, viscous liquid. But there are other ways that we could represent it too, using a ball and stick model, or this is something that's referred to as a Haworth projection. But again, these are all different ways of representing information. It's our symbology if we think back to our chemist triangle. So if we think about our norms, again, it's really important that we have a space where everyone can learn. It's important for all of us. And so we really appreciate your questions. In fact, I noticed this week that because of the questions that you asked in class, there was a deeper learning that occurred. So thank you for those of you who were brave and asked questions. Being able to know that you can rely on others. So part of our ability as scientists to do the work that we do is because we can collaborate together. And that includes checking our work, helping catch mistakes, but also being able to ask questions to help each other understand what makes sense and maybe what doesn't. And then we've talked about iterating, this willingness to take a risk, to try again. And then I've been putting a big emphasis on this idea of ownership or agency, this idea that we can self-regulate our learning. So if we think about designing and implementing methods of gathering information and data to answer a question, we're going to balance the following chemical equation. So I have iron, which is a solid metal, I have oxygen, and then I have iron oxide. And so in order for us to have 4 irons, I need to multiply by 2 because I have the subscript 2. So 2 times 2 is 4. That means I would have to put a 4 here. And then 2 times 3 is 6. And I would have to put a 3 here so that my oxygens would balance. We shared out about Rafael San Miguel. He's a really phenomenal chemist who is deaf actually from birth. And so he went to Texas A&M and originally started working for NASA, but ultimately wanted to become a research and development scientist. And so he moved to and has worked for Coca-Cola as a flavor chemist. What's really interesting about that is that he said that although he does not have the ability to hear, his other senses have been heightened, and so he does have the ability to taste, and that his heightened sensitivity there is part of what allows him to serve as a consultant for example, a Boston area food incubator startup called Chew. He's also the board member of the Atlanta Speech School, and he's a Points of Light volunteer, and he was recognized by Michelle Obama in the White House as a champion of change. I think he's a really great example of a scientist that we want to spotlight. If we think about our learning outcomes for Chapter 4, there's a couple of things that we're going to do that are really critical in Chapter 4 to pretty much all of the work that we do in chemistry. So the first is balancing chemical equations. We're going to use balanced chemical equations to convert between amounts of reactants and products. And then we're going to use molar concentrations to convert between volumes and moles. We're going to identify limiting reactants, and then we're going to calculate theoretical yield and percent yield of reactions. So these are really critical because each one of these is going to allow us then to engage in and make sense of the reactivity of other molecules. So if we think about balancing equations, there's a couple of key pieces of information that we want to be attentive to. Our reactants are on the left and our products are on the right. We want to make sure that our phases are in parentheses and that the coefficients that we use in order to be able to get the same number of atoms of each element on the left and on the right. So if we think about this representation, The balanced chemical equation is really what we see using the molecular formulas. And so we've called out what are reactants and coefficients. But it's important to think about the fact that those represent three-dimensional molecules, right? So while we use the symbology to represent our atoms in the periodic table, it's really important that we recognize that these have, they take up space. They're three-dimensional, and they're differentiated also by size because of the number of electrons and protons, their atomic characteristics. So if we think about balancing our equations, then we're going to start with an element that is only in one reactant and one product if possible. And then where possible, we're going to balance ions instead of elements. And then when present, we're going to save diatomic oxygen for last because that will make balancing easier. So if we think about designing and implementing how we gather information and data to answer a question, there's kind of three pieces we're going to think about for our balanced equations. There's the molecular balanced equation. This shows all compounds as neutral formulas. Then there's the complete ionic. This shows compounds as they actually exist in solution. And so molecules and insoluble ionic compounds are neutral compounds. And then we have soluble ionic compounds that are aqueous ions. And finally, we have our net ionic. This shows only the species from the complete ionic equation that actually react. And so the key here is that we don't include spectator ions. So anything that's the same on the left-hand side of the equation as what we see on the right-hand side of the equation are spectator ions. They haven't changed their phase. And so we know that they are not part of our net ionic equation. So it's really important when we're thinking about these ionic equations to think about why is it that we even have ions in the first place? So how do ionic compounds dissolve in water? And so if we think about water, we think about the fact that oxygen has a partial negative charge and hydrogen has a partial positive charge. That partial charge is because of the distribution of electrons. And so if we think about then the way that that water molecule would orient in solution relative to an ion like sodium and chloride, you're going to notice something. The positive, partial positive, so in this case, the hydrogen side of the water molecule, orients towards chloride, where the oxygen, or the partial negative side, orients towards sodium. And so our slightly positive hydrogens are attracted to the chlorine anions, whereas the slightly negative oxygens are attracted to the sodium cations. And so if we think about then how this would behave in an actual solution, we have our sodium chloride, and it becomes dissolved, where these ions are separated away from the solid, and they become surrounded by water molecules. So how do molecular compounds dissolve in water? Well, if we think about the difference between salt and sugar, salts, which are also referred to as electrolytes, dissociate into ions when they dissolve. So if I were to put solid salt into water, it would eventually become separate ions. So the positively charged sodium would be surrounded by water, and the negatively charged chloride would be surrounded by water. That's different from a sugar solution. These are non-electrolytes. These are molecular compounds that do not dissociate when they dissolve. That's an important distinction because as we think about how to write out our equations, we want to make sure that we're being attentive to details like our phases. So we're going to think about how to write out a molecular equation, a total ionic equation, and a net ionic equation. So if we think about that, so we have 3 sodium hydroxide, which is aqueous, plus iron chloride, which is also aqueous. And that's going to form iron hydroxide plus sodium and chloride. So if we think about our solubility rules, which we had it out in class, one of the things we'll notice is that hydroxides are insoluble. So that's the reason why there's a solid here. And then if we think about taking this equation and separating it out into its ions, right, our 3 sodiums becomes 3 sodiums plus, which is an aqueous ion. But that 3 also applies to the hydroxides. We have 3 hydroxides that are aqueous, negatively charged ions. And then we have iron 3 plus, which is aqueous. And we have 3 chlorides, which are also aqueous. Then Our iron hydroxide, because it is a solid precipitate, stays together. It doesn't get separated out into its ions. And then we have our 3 sodium ions and our 3 chloride ions. So one of the things you're going to notice here is that I can cancel my 3 sodiums because they're the same on the left as they are on the right. And I can do the same thing for my chlorides, the same on the left as they are on the right. And then what I'm left with is my net ionic equation. So in this case, my 3 hydroxides plus my iron goes to my iron hydroxide. This is what we can refer to as a double displacement reaction because I am literally swapping, right? My sodium goes with my chloride, my iron goes with my hydroxide. So we're going to look at a couple of other examples. So we're going to look at an example of a strong acid and a strong base. And here, if we're thinking about how to represent that equation, so our strong base is sodium hydroxide, and our strong acid is HCl or hydrochloric acid. And the really important piece here is to understand that when we say the word strong, we mean that they dissociate completely in water. So that means they only become ions. They don't stay together as sodium hydroxide and HCl. When they go into solution, they completely become sodium positive ions, hydroxide negative ions, hydrogen plus ions, and Cl minus ions. And that's really important because when they dissociate completely, that is what allows for the formation of water, as well as the formation of salt, in this case, sodium and chloride. So again, we're going to think about canceling our spectator ion. So anything that is the same on the left as it is on the right, we're going to cancel. And that leaves us with our net ionic equation, which in this case is the formation of water. And this is characteristic of the reactions between an acid and a base. So this is an acid-base reaction. And if you're wondering, well, what makes something an acid? What makes something a base? An acid is anything that has a proton that can be deprotonated. Right? And then we have a variety of different ways that we think about bases. One of the ways we can think about bases is as hydroxide ions that have a negative charge. If we think about then the interaction between a weak acid and a strong base, if we think about strong acids as something that completely dissociates or ionizes completely, then something that's a weak acid actually stays in its molecular form. So HF, for example, is the only halogen that is a weak acid. All other halogens are strong acids. And what's really interesting about HF is that it stays, right? It's loath, it doesn't want to give up the hydrogen because the fluoride is the most electronegative, and so it wants to hold on to that proton. So if we think about how we might balance then and write out the ionic equation, right? Our HF, when it dissociates, becomes H plus and F minus. And then it reacts with KOH, so K plus and OH minus. And it goes on to form KF and water. So now this is really interesting, right? Because we know that HF doesn't completely dissociate. So it's only some of the time that we see these ions H plus and F minus as our aqueous ions. But our KOH is a strong base, so it dissociates completely all the time. And then we have K plus and F minus and water. And so if we think about the spectator ions, our potassium, which is our K plus, and our fluoride, which is our F minus, cancel. And we're left with, again, this formation of water, which tells us that, again, this is an acid-base reaction. And the last example we're going to look at is a strong acid and a weak base. So again, our strong acids completely ionize, but our weak bases are mostly molecular, so they stay together. And if we think about how we might write out this equation, right, here's our strong acid, and here's our weak base, and here's our product. So when it ionizes, we form H plus, which is an aqueous ion, the ClO4 minus, which is also an aqueous ion, and then our ammonia stays mostly together because it is the weak base. We form ammonium, which is our positively charged cation, and then our ClO4 minus, which is our negatively charged anion. And so our anions can cancel because those are the same on the left as they are on the right. And what we form is ammonium. So our H plus NH3 goes to form ammonium. Again, this HClO4 is an oxy acid. It's a strong acid and it completely dissociates. And so again, this is also an acid-base reaction. So if we think about how we might balance equations and then think about their ionic and net ionic equations, here are 3 examples that we can work through for additional practice. So the first one, I have silver nitrate and sodium sulfate, and that's going to react to form silver sulfate and sodium nitrate. And so here I have to make sure that I'm balanced in terms of all my atoms. So I have a 2 here as well as a 2 here. And so when I write this out, I should have 2 silver plus 2 nitrate plus 2 sodium plus sulfate. And that's going to go on to form Ag2SO4, which again, based on our solubility rules, we know is going to be a solid precipitate, plus 2 sodiums plus 2 nitrates. So if I think about my spectator ions, my nitrate and my sodium both cancel. And so I'm left with silver sulfate, which again, this is a double displacement reaction. If I think about the next example, so this is HCl plus calcium carbonate. It's going to form carbonic acid and calcium chloride. And again, we want to make sure that our equation is balanced. So we have 2H plus and 2Cl minus plus calcium carbonate, and that goes to form carbonic acid plus calcium chloride ions. So if we think about our spectator ions, the only ones that are spectators in this case are our chloride ions, because again, the calcium is part of this solid, so it has a phase change, whereas here the calcium is aqueous, and so we want to make sure that we include the calcium as well in our net ionic equation. This is really important to note. In the presence of a strong acid, carbonic acid is going to form carbon dioxide and water, which is what's shown here. So when we think about this net ionic equation, well, we might be tempted to represent carbonic acid as the product. In reality, we're going to form water and CO2. And again, this is an acid-base reaction. The last example is an example of a combustion reaction. So this is methane gas in the presence of oxygen, and it's going to generate carbon dioxide and water. And so notice here, right, we're used to seeing water as a liquid, but in this case, combustion creates water as a gas or water vapor. And again, we want to make sure that we have a balanced equation. So we should have a 2 here. Ooh, let me fix that. Make sure that you put a 2 here in front of your water. Our science practices are asking questions and defining problems. We want to make sure we analyze and interpret data, and then constructing explanations or designing solutions, and then engaging in argument from evidence. So if we think about precipitation reactions and solubility, our soluble ionic compounds dissociate in water, whereas our ionic compounds tend not to dissociate, and we call them insoluble compounds. And so you can actually see 4 different examples of precipitates here, where those materials are actually crashing out of solution and forming solids. So the things we know are always soluble are compounds that contain group 1A metal cations, ammonium, nitrate, chlorate, perchlorate, and acetate. These are always going to be soluble, and they have a tendency to make other things soluble too. Things that are usually soluble are compounds containing chloride, bromide, and iodide, except for when these are paired with silver, mercury, or lead. And then generally insoluble are compounds containing carbonate or phosphate, except when they're paired with group 1A metals and ammonium. And then hydroxide or sulfide, again, except when they're paired with group 1A or 2A metal cations and ammonium. Our silver ion, lead, and mercury are always going to be insoluble, so they're going to have a tendency to crash out of solution. So which of the following compounds would dissolve in water? If we think about our solubility rules, we know that Sodium is a group 1 metal cation. So we know that that's going to be soluble. We know that chloride is something that is also going to be soluble because it is paired with that group 1 metal cation. So they're both soluble. The potassium carbonate is going to be soluble because of this group 1 metal, again, potassium. The calcium carbonate is not going to be soluble. So even though these are all three white solids, even though they all have a powdery nature to them, because of their chemical properties, they're going to behave differently. So one of the things we're going to think about this week in lab is the theoretical yield. That's a really important concept in chemistry because what it is it's the most product that you could possibly get from a reaction, or the maximum yield. Yield just being the amount of product that you could get. So if we think about calculating the theoretical yield in grams for a reaction, let's say that we had 0.4985 grams of copper, we had excess sulfur, and we're wondering how much copper sulfide we would get. So the process that we would use for solving this problem is to convert our grams of copper to moles of copper. And then we would use the mole ratio of our balanced equation to be able to find the moles of copper sulfide. And then we could find the grams of copper sulfide from that. So if we think about that calculation then, we would need to balance our equation first and foremost. We always want to balance our equation. So we have 16 copper plus S8, and that's going to form 8 Cu2S. And so that's our balanced overall equation. Then we're going to do a conversion where we're going to start with 0.4985 grams of copper. We know the molar mass of copper, which gives us the amount in moles of copper. And then we know that we have 16 moles of copper for every 8 moles of copper sulfide. This is what we call a molar ratio. The molar ratio is what allows us to convert between different reagents or different products. Once we have moles of copper sulfide, then we can convert using our molar mass to grams. And so in this case, we would get 0.6243 grams of copper to S, or copper sulfide. And so in order to be able to solve this type of a problem, one of the things that we're always going to have to be able to do is to find the molar mass of whatever chemical we're working with. So in this case, to find the molar mass of copper 2 sulfide, we know that we have 2 coppers, so 2 times 63.55 grams per mole. And then sulfur's molar mass from the periodic table is 32.06 grams per mole. If I add those two together, that's how I get this number 159.17 grams per mole for Cu2S, which is what goes here, right? 1 mole of Cu2S is equal to 159.17 grams of Cu2S. So again, thinking about our setup, the first thing we do is balance our equation. And then we think about the process that we use to convert from grams to moles. Then we use a molar ratio to find moles of our product. And then we can convert using our molar mass to the grams of that product. If we think about percent yield though, in reality, right, our theoretical yield is the maximum yield that's possible, but percent yield is what actually happens. So if the actual mass of a compound was measured at the end of the experiment and we got 0.5432 grams, then to be able to calculate the percent yield, we would use the following equation. So we know our theoretical yield based on a calculation. This is the maximum amount possible based on our limiting reagent. And then 0.5432 grams of copper sulfide is what we actually got. And so we put our actual over our theoretical and we multiply by 100. So 0.5432 grams divided by 0.6243 grams, then we multiply by 100. And that gives us 87.01%. And that's the actual yield that we got from our reaction, or our percent yield, because it's reflective of what we were actually able to obtain. So again, our process for calculating percent yield is it's always our actual yield in the numerator and then our theoretical yield in the denominator. If for some reason, right, our numerator is bigger than our denominator, that means that we got more than 100%, which isn't possible. So that means that there must be some contaminant in our product. So technically, we're looking for a number that's less than 100%. So if we think about stoichiometry and limiting reagents then, if we're given the masses of more than one reactant, what do? This is going to be a limiting reactant problem. So in order to be able to solve this problem, we're going to calculate how much product you would get based on each reactant. And then the one that gives you the least product is the one that runs out first. This is the limiting reactant. And this is what we use for calculating our theoretical yield. So let's look at an example to make sense of that. So if I'm burning 10 grams of hydrogen gas with 15 grams of oxygen gas, what's my theoretical yield? So I'm going to do two different calculations. I'm going to calculate the amount of product that's possible when I start with grams of hydrogen. And then I'm going to do a similar calculation, but this time I'm going to think about the amount of product that's possible when I start with my grams of oxygen. So let's think about what that calculation actually looks like. So the first thing we have to do is always balance our reaction. We're always going to start with a balanced equation. Then we're going to take what's given in the problem, so our 10 grams of hydrogen, and we're going to find the molar mass of that molecule from our periodic table. So 1 mole of hydrogen is equivalent to 2.016 grams of hydrogen. Then from our balanced equation, we're going to find our molar ratio. So in this case, right, I have 2 moles of H2, right? And I should have a 2 here, right? Because this needs to be balanced. So I have to have a 2 in front of my water in order for this to be balanced. So this should be 2 moles of H2O because I need 4 of hydrogen overall. So if I think about that, then my molar ratio is 1 mole of H2O for every 18.016 grams of H2O. So that's going to be equal to 89.4 grams of H2O. And then if I think about doing that same calculation, again, I have 15.0 grams of O2. And so the molar mass of O2 is 32. So 1 mole of O2 is 32 grams of O2. And again, I use my molar ratio from the problem. So I have 1 mole of O2 for 2 moles of H2O. And that's going to give me 1 mole of H2O and 18.016 grams of water. And so when I multiply across the top and divide by everything that's on the bottom, I have 16.9 grams of H2O. So if we're thinking about these two, we always want to choose the smaller number. Even though it's tempting to say the maximum yield, you might think you want the bigger number. In this case, you can only make as much as you have the limiting reagent of. So you always want to choose the smaller number. So again, our balanced equation should have a 2 in front of the hydrogen and a 2 in front of the water. When we do our calculation, we're going to find that our limiting reagent is the one that has the lower amount. That's going to be our theoretical yield. Just a quick reminder, student success will meet after class. So this is Mondays and Wednesdays after class. And there are actually other times. So if that time doesn't work for you, there are other times that are available. And then in discussion, we'll be working on stoichiometry especially and balancing equations today. And then the last 5 minutes of class, you're going to organize your goals, you're going to think about your thinking, and then you're going to reflect on your learning. So take a moment, check in, see where you're at. Think about what it is that makes sense, what might need a little bit more practice, and then what might be something that you could think about for your next steps. And then next week, we're going to wrap up stoichiometry. So we're going to finish chapter 4. And then really importantly, you're going to have your exam on Wednesday. That's chapters 1 through 4. When we're done with the exam, the next chapter we're going to be working on is chapter 9. All right, thanks so much. Have a great one.